All right, so 2.1, basics of functions. And like I said, this note right here is for me. So let me know where we're going. Once again, the title is Basics of Functions, but I wrote these notes, the first part of these notes right here. And it starts off with the definition of a relation. A relation is any set of ordered pairs. So here we have an example of that. So it's 1, 2, 3, 4, 5, 6. We have 3 ordered pairs. So that will be considered a relation. Your domain is the set of all first components of the ordered pairs. In this case, that would be 1, 3, and 5. Your range is a set of all of the second components of the ordered pairs. In this case, that'll be 2, 4, 6. All right, so next we're looking at a comparison of the two. Just want to make sure everything's copied before I scroll all the way up. All right.
Can you go back up? Can you go back up a little bit?
Uh,
Yeah, right there.
all right, are we good to go? Straight, straight. All right. So domain, the comparison to the domain, comparison of the domain to the range. The domain is your first component, range is your second component, as we mentioned already. So that means your domain will be your x variable, so your x values, range will be your y values. Domain is your input, range is your output. Domain will be your independent variable, range is your dependent variable, and then that also makes the domain lie on the horizontal axis, or your horizontal move on your range would be your vertical axis. All right. Oh, someone said something in the chat. Oh yeah, no problem. Not a problem at all. All right. Can I scroll all the way up? Good, good. All right. So, definition of a function. A function is a relation in which the elements from the domain corresponds to exactly one element in the range. So elements from the domain correspond to exactly one element in the range. All right. So here, determine whether each relation is a function. So we have 1, 6, 2, 6, 3, 8, and 4, 9 as ordered pairs of this relation. Now I'm going to erase this stuff and we'll walk through how we determine whether it's a relation, whether it's a function or not. All right. So our domain is 1 through 4, 1, 2, 3, 4. Our range is 6, 8, and 9. Okay. So now the definition of a function is that each element in your domain go to exactly one element in the range. So you would look at each one of them individually and ask yourself, is it going to just one value? So when I look at 1, is 1 just going to just one value? The answer is yes. Look at the number 2, is 2 going to exactly one value? The answer is yes. Now 1 and 2 are going to the same value, but individually they're only going to one value, so that's okay. The statement is that each element in your domain is going to exactly one element in the range. So number 3, is that going to one value? The answer is yes. And is 4 going to one value? The answer is yes. So since each one of them go to exactly one value in the range, then yes, it is a function. All right. Questions. So you can do a mapping like this if you want, or if you have it laid out this way as far as your relation is concerned, and just analyze each individual element in your domain, see if it goes to one element in the range. If it does, then it is a function. All right. I scroll up. All right. That's not everything. Here's the next one. So here we have 6, 1, 6, 2, 8, 3, and 9, 4. So once again, set up your domain, set up your range, And you can do a mapping in the same fashion that we did in the last one. You want to ask yourself, is each element in your domain going to one element in the range? So we have 6 going to 1, but then 6 is also going to 2. So that's what we don't want to happen. We have 6 going to more than one value. So that stops it from being a function. So your elements in your domain has to go to one value or one element in the range in order for it to be the function. Cannot go to more than one. And then 6 goes to 1 and 2. So no, it's not a function. Questions on that before we come to some conclusions about functions, just in case there were some extra thoughts about it. Hopefully what I write next will help us to clear out our thoughts on functions, what is and what is not a function. So looking at what we had here in these two examples, we recognize that there can be a repeated value in the range, but no value can repeat in your domain. So if you notice, going back to that first one, we had 6 that repeated in the range, and that was a function. But when 6 repeated in the domain, that was not a function. And so that's what we mean by that. There could be a repeated value in the range, but no value can repeat in your domain. And then here, the range can go to more than one value. The domain can only go to one value. So that goes back to what we mean by repeating in the range and versus the domain. Any questions before we go to the next one? All right, is it for that? So problems before I switch to the next page? By still holding on to these statements. All right. All right, so here, the next one, they're asking us to determine if we have a function, if the equation define y as a function of x. So the last time we had a relation, we just had a set of ordered pairs. This time we actually have an equation that we want to determine whether it is a function. So our first.
So what would this be called?
Oh, just this is directions right here. Just determine whether each is a function that defines
No, like
y.
I be having headings for every like 1.1, 1.2.
You think
So
you be
we're saying
having,
2.1.
say that one more time, man?
You know how like we have like domain function or like I have a different heading for everything that we go over. So does this have its own heading or is this still under domain function?
Oh, this is still domain. Yeah, this is determining, because if you go back to what we did, let me go back to that last screen. So here we were determining whether each relation is a function. So now we're determining, oh, going to the wrong one. Sorry about that. 161. Now we're determining if this equation is a function. So before we just had a relation. Remember, a relation is just a set of ordered pairs. So we were trying to determine if that relation was defined as a function. Now we're trying to determine, is this equation defined as a function? All right. Is that what you were asking? What kind of heading you were
Yeah, I
putting?
got it. I got it.
Okay, cool. I'll just make sure I answered your question. All right. So this is the first question that we're looking at, or the first equation that we're looking at. We're trying to decide if it defines, or if it's defined as a function um, of x. So we want to solve it for y, because it says define y as a function of x. So we want to solve it for y. So I subtract the x squared from both sides, and I have the equation y equal to 4 minus x squared. So I'll let you copy that down before we go to the next step. So if you want to define or see if an equation defines y as a function of x, you have to solve it for y first before you do your evaluation. So then, looking at step 2, you want to evaluate to see if multiple values of y can be produced. So I'll show you what that means in a second. Now we'll also have, when we go down a little further, we're going to go through the vertical line test, which we could just throw this in a graphing calculator or a graphing tool to see if it'll give us a function or not. But until then, you can analyze your function by plugging in x values and see what type of y values you get out. Now, remember, what will cause this to not be a function is if my x will produce more than one y value. So when I plug in 1, I get out the singular value of 3. When I plug in -1, I also get 3. And when I plug in 2, I get 0. So those are just examples of what would happen when you plug in your values. No matter what value you plug in, only one y value will be produced. And the next example will show you what I mean by producing more than one y value. But we see that every time we plug in a value for this one, only one y value is produced. And so that means that this is a function. So once again, the process is you solve the equation for y, then you plug in x values or analyze your equation to see if when you plug in x values, would you get more than one y value out. In this case, each time you plug in an x value, you're only going to get one y value. So it means that this is a function. All right, so let's look at the next one. So now here we have a very similar equation, but this time y has a power of 2 on it. So it's x squared plus y squared plus x squared plus y squared equal to 4. Now, what's going to be key here is that you have an even power that is on your y. So that's going to be key, because when I go to solve for y, remember that's our first step, is that we subtract x squared from both sides. Then if you take the square root of both sides in order to get that square off of y, because of the square root property, we're going to have plus or minus square root of 4 minus x squared. And that's because we had that even power on y. All right, and in a second, we'll see how that makes a difference in what we do. All right, scroll up, everybody good. All right, so now that we have that plus or minus there, remember that plus or minus represents the positive result and a negative result. So that when I plug in, let's just use x for 1, I would get out positive and negative square root of 3. So I'm getting out two results when I plug in the number 1. So that means x produced 2 y values, and that means that this is not a function. So the key to it is that I had an even power on that y initially, and that made or put us in a position in which we had to have that plus or minus there, and that will produce multiple y values. All right, questions? Any questions? All right, any problems before I scroll up? All right. So the next one is vertical line test. If any vertical line crosses or touches a graph more than once, it is not a function. So once again, the vertical line test, if a vertical line crosses your function more than once, or crosses your graph more than once, then it is not a function. So if we look at a circle, that's not a function because when I draw a vertical line through it, it crosses it twice. Your linear equation, it's just a straight line, so it's only going to touch it one time no matter where I draw a vertical line. Your parabola, same type of situation, no matter where I draw a vertical line. It's only going to touch it once. And then this graph down here on the bottom, even though if I touch it over here, it hits it only once, right here we'll hit it 3 times, so that stops it from being a function. All right. Questions, questions, questions. All right, questions on that. All right, so next one is function notation. Here we have f of x. That's how you would say that, f of x. And so y is equal to f of x. Those are interchangeable. And from this point forward, they would expect you to know that, and they wouldn't say anything about it. You know, y and f of x can be switched at any given point in time, and they would expect you to be okay with that notation. So y equal to 2x plus 1 is the same thing as f of x equal to 2x plus 1. It's just that f of x equal to 2x plus 1 is actually considered function notation. All right. Once you put the f of x there, that's considered function notation. So what that allows for us to do is to give instructions without actually having to say much. Notice here it says find f of 3, but even if it didn't say find f of 3, if you wanted to know what f of 3 is, then you look at f of x, and that means you'll plug in 3 into the function. And that's all that means, that you'll take f of x and plug 3 into the function. And that's what we're doing right here. So you have f of 3 is equal to 2 times 3 plus 1. 2 times 3 is 6, plus 1 is 7. So if you see f of 3 is equal to 7, that's also the same thing as telling us that our ordered pair is 3, 7. Because you plugged in 3 for x and got out 7, and that is your y. All right. Questions on function notation. All right, scrolling up. First example, we have f of x. If f of x is equal to x squared plus 3x plus 5, find f of 2, and then find f of x plus 3. All right. So f of 2 just means we're going to take 2 and plug it in where we see x. So that's right here, right here. So f of 2 is 2 squared plus 3 times 2 plus 5. 2 squared is 4. 3 times 2 is 6. 4 plus 6 plus 5 is 15. All right. Problems with that. Now, f of x plus 3 means we're going to take x plus 3 and plug it in where we see x. So we're going to take that expression of x plus 3, plug it in where we see x. And that's what we did right here. So we have x plus 3 squared, 3 times x plus 3 plus 5. Now don't forget you have to expand this. You can't just square x and square 3. And so that's what I did over here. Went ahead and multiplied that out. So x plus 3 times x plus 3, x times x, which is x squared, x times 3, and then 3 times x, and then 3 times 9. And that gives us x squared plus 3x plus 3x plus 9. Add your like terms in the middle. That gives us this expression right here, x squared plus 6x plus 9. And then you distribute this 3. And that'll give us 3x plus 9 right here. And of course, that 5 is still in the back. After you fully expanded your expression, you combine your like terms to simplify it. 6x and 3x will give you 9x. 9 plus 9 plus 5 will give you 23. All right. Questions? All right. Any questions before we, let's see, what time is it? Get out of here at 12:15, right? Yep. So at least start 2.2. All right. So 2.2, more on functions. Like I said, we'll at least start this even if we don't finish it. Increasing, when you have a function that's increasing on an open interval, that just means that as the x value increases, the y value increases. So we read it from left to right. So as we go to the right, your function is going up. So the red arrow is following it going up. And then the opposite happens for decreasing as you go from right to left. I mean, left to right, excuse me, left to right. Um, as x increases, your y decreases. So your function will be going down. All right, so for constant, as the x value increases, the y value stays the same or stays constant. So you have a constant interval. That's what that would be. All right, give you a chance to finish writing constant before I go to the example. All right, so here we have state the intervals on which each is increasing, decreasing, or constant. So notice what I said right here is that we're going to use the x values. You use x values in order to state your intervals. Remember, we're reading this from left to right. And remember, we're not going from up to down. We're reading it from left to right. So we're using our x values to create our intervals or to state what our intervals are. So if you look at this first one, from left to right, it is going up. And it's doing that to this number right here, which would be -2. So from negative infinity, we're talking about coming from the left side up to -2. Our function is increasing. So once again, from left, talking about negative infinity up to -2 is increasing. Then from -2 to +2 is constant. And then from 2 to the right, remember to the right will be positive infinity. That means it's decreasing, it's going down. All right. So that's how we have, that's how we got these intervals over here. And once again, these are set up because we're reading from left to right. That's why we're going from negative infinity to positive infinity in this case. And we just need to break it up according to our intervals. How is your function behaving in each interval? All right, so in B, we're doing the same thing. It will also notice we use parentheses for all of these because they're open intervals. So when you say open intervals, you're using that parentheses, not the bracket. So now for the next one, once again, we're coming from the left. But as we come from the left, we're going down to this point right here, which is our origin, that's 0. So that's why we have this negative infinity to 0 as decreasing. Then from 0 to 2, we're increasing. And then from 2 to positive infinity, remember we're going to the right, that would be decreasing. And we don't have a constant interval in this case. All right, questions on that? All right, so relative extrema. So if you're talking about relative max, relative maximum, that's the maximum value relative to an interval, to an open interval. And then relative minimum is the relative minimum, is the minimum value relative to an open interval. So maximum value, largest value versus smallest value in the minimum in an interval. So the reason why we say in an interval, because notice that this goes, let's see if I can erase this without erasing that. Yeah. So this graph goes to positive infinity, goes up, and it goes down to negative infinity. So there's no real legitimate maximum or minimum because it's going to continue to go up to infinity and go down to infinity. So if you wanted a relative minimum, something like this value right here could be your relative minimum. Relative maximum. That's the largest value or the highest value in that interval. And then down here would be like a relative minimum because that would be the lowest value in that certain interval. So it just depends on where your intervals are, where your highest value and your lowest value would be. If I chose this interval right here, then this would be my highest value and this would be my lowest value, So it just depends on what you're analyzing in a graph, in a chart. But it would just be the highest value in an interval or the lowest value in an interval, the max and your min. All right, questions, new questions. All right, definition of symmetry. So we're looking at the symmetry with respect to the y-axis. It says for every point on the graph, the point negative xy is also on the graph. So the way we would test that symmetry is we would substitute negative x for x in the equation. And if it results in the original equation, then it would be symmetric with respect to the y-axis. Let me know if I scroll up too early. Okay. Symmetry with respect to the x-axis. For every point on the graph, the point x negative y is also on the graph. And the way we test that symmetry is to substitute negative y in for y, substitute negative y in for y. And if the equation results in the original equation, then it's symmetric with respect to the x-axis. All right. Got one more. Then symmetric with respect to the origin for every point on the graph. The point negative x, negative y is also on the graph. And the way we'll test for that is that we'll substitute in negative x for x, substitute in negative y for y into the equation. And if it results in the original equation, then that means it is symmetric with respect to the origin. All right, questions? Any questions? All right, so let's try this out. So it says determine whether the graph of x equal to y squared minus 1 is symmetric to the y-axis, x-axis, or the origin. Anybody holding on to that? I scroll all the way up. Okay. So first one, it doesn't matter which one you find first, which symmetry you prove first. So I'm looking at being symmetric to the y-axis first. So you have to substitute in negative x for x into the function. So I did that right here. Put negative x in for x. So that's negative x equal to y squared minus 1. So I want to make a clean comparison to the function that I have up there. I have x equal to y squared minus 1. So if I multiply both sides by negative 1, just so I can say x equals, once again, I want to make a clean comparison, x equals. So I did the same thing, put it in the same form, and that's what I have right here. Multiplying negative 1 to each term, x is equal to negative y squared plus 1. And so the statement after that, since it is not the original equation, the function is not symmetric with respect to the y-axis. So when you plug in negative x, after you simplify and when you make your comparison, it should equal the original equation if it is symmetric to the y-axis. Any questions before we look at the next one? Scroll up. All right, next one, symmetric to the x-axis. So in this case, you will substitute in negative y for y and do the same thing, simplify, and then make a comparison to the original equation. So I plug in negative y. So negative y squared, don't forget the effects that a square have on a negative. That will be negative times a negative, which will be positive. So that simplifies to x equal to y squared minus 1. And since this function is the same as the original, it is symmetric with respect to the x-axis. All right. Questions? Any questions? All right. Last one, symmetry to the origin. We have to plug in negative x for x and negative y for y. And that's what we did right here, plugging in negative x and negative y. So we already talked about how negative y squared is just going to be y squared. So that's what happens here. And then once again, I want to multiply both sides by -1 so I can have x equals. And doing that, that gives me x equal to negative y squared plus 1. And since this function is not the original, it is not symmetric with respect to the origin. All right. Any questions? Any questions? We got even functions, odd functions, difference quotient. Let me see what 2.3 is. 2.4. Okay. All right. So last thing for today, we'll look at these even functions and odd functions. They kind of flow with the same thing that we just finished doing. And then we'll stop here in 2.2. So if you want to determine if you have an even function, you'll take negative x and plug it into your function. If it gives you your original function, then it is even. Odd function, if you plug negative x into your function and it gives you the opposite sign of your original function. Each term in your function now has the opposite sign than the original function, then it's considered odd. All right, so that's how we would determine if we have even functions versus an odd function. Once again, when you plug in negative x, when you simplify it, if it gives you your original function, then it is even. If you plug it in and each one of your signs are opposite the original function, then it is odd. All right. So we want to determine if it's even, odd, or neither. So this first one right here, we have f of x is equal to x cubed minus 6x. You plug in negative x into both of them. Don't forget the effects that an exponent, an odd exponent has on a negative versus an even exponent has on a negative, and that's what I tried to express over here on the right. You know, if it's even, you're always going to result in a positive result. Let's see, yeah, there you go. If it's even, it's always going to result in a positive, or always going to have a positive result. So -1 squared will be +1. But if it's odd, you will always have a negative left over. So it's always going to give you a negative result. So if I have -1 to the 400 power, I know my result is going to be a positive because 400 is even. And then at 505, if I have -1 to the 505th power, the result is going to be -1 because 505 is odd. So going back to what we just did here, with x cubed minus 6x. X cubed, negative x cubed would result in negative x cubed. And then here, negative 6 times negative x is positive 6x. And if you compare that to your original equation, it says since each sign is opposite the original function, this function is odd. All right, next one. We have g of x is equal to x to the fourth minus 2x squared. Plug in negative x into the function. We have even powers. So negative x to the fourth is going to be positive x to the fourth, and negative x squared will be positive x squared. So this function is the same as the original, and that means it's even. All right. Questions before we look at the last one? All right. So h of x is equal to x squared plus 2x plus 1. And plugging in negative x. Plugging in negative x into each one. And we see negative x squared is just going to be x squared. Then we have 2 times negative x, which would be negative 2x plus 1. So all of our signs are not the same. Neither are all signs opposite. So this function is neither even or odd. It's not even or odd. All right, questions? Any questions? All right, is everybody good? All right, so we have one more thing that's in 2.2, and we will do that next class. It's called the difference quotient. So we'll do that next class. Don't let me forget. Don't let me jump into 2.3 and not do the difference quotient. That's the last thing in 2.2. But any questions before we close out today? All right. So you guys have a great weekend. Be safe. And I will see you on what? Monday. I'll see you on Monday.
Bye. Have a good weekend.
All right. Take care. You do the same. Thank you. All right. Do the same. Do the same.